Here's a big truth. The universe is awfully big, so colossal that we're not allowed to gaze at it live and direct. Light takes such a long time in crossing the enormous distances and getting to us that when it hits our eyes, we see the cosmos really late. The moon? 1 second later. The sun? 8 minutes later. The closest star? 4 years later. The nearest great galaxy? 2 million years later. We don't contemplate the universe as it is now. We see how it was. Celestial bodies that we can see today may no longer exist. Looking up to the sky is looking to the past. But at the end of the day, this is a fun idea. Because if the farther you observe, the longer you go into the past, does this mean that if I look far enough, I'll be able to see how the cosmos was when it was just a newborn? Can the primitive universe be seen in that way? Well, reality is a little bit more complex than that. Once we penetrate into deep space, the cosmos seems to rewind. The big structures blur, the temperature rises up all of a sudden, matter becomes a very big cloud that for a while doesn't shine much until it intensely lights up, and then darkness. The image shuts off. When we get to a certain distance, we cannot see anything else. That means that this very last light is critically important. If you capture it and express it in a photograph, something like this appears. Exciting, right? As boring as it may seem, this is the oldest picture of the universe. Of the universe means that there is not an older picture of it, but also that this is how the primitive universe looked, the same everywhere. This picture has a name, the cosmic microwave background. Yeah, background because there's no light behind it, and yeah, microwave. This light has been traveling towards us for so long that the expanse of the universe has stolen a lot of energy from it until leaving it the color of the microwaves. One warning, if someone tells you that the microwave background is the echo of the Big Bang or the light of the Big Bang, you can kick them on my behalf. It's not the light of the Big Bang. It's the light emitted roughly 400,000 years after the Big Bang. Omitting those years is a true crime. I assure you lots of things happened in that time. And related to this, what makes that moment special? Why isn't there an older light? The answer resides in how the primitive universe was a land of few liberties. At this time, the cosmos was so dense and hot that atoms couldn't exist. Protons and electrons had so much energy that they danced separately in this primeval plasma. This was annoying for the light that lived there because it cannot help interacting with electrically charged particles. As soon as the light tried to move, it encountered a proton or an electron that absorbed it. Light rays weren't very good at crossing a long distance before a charge trapped them. They were prisoners of that plasma. Light was coupled. But everything comes to an end. The expansion of the universe reduced temperature, and electrons and protons stood still enough so that attraction worked and the first atoms could be formed. This little period is called recombination. Since the electrons shield the core, the ensemble seems to not have any charge. The light, not having charges to bounce off, is liberated from the plasma, and that's how its travels began. So during the very birth of the atoms, the light hit the plasma one last time and shot off. Some of these rays would end up colliding again, but others would go their way without interactions, traveling through space for billions of years until they ended up in the Earth. This is the cosmic microwave background. So the reason why we cannot see something prior to that is the primitive habitat prevented light from going all the way to end up here. But we have talked only about pictures of the universe taken with light. Physicists think that even older pictures can be obtained if we use other things, such as neutrinos. As it happened with light, neutrinos also decoupled from the plasma, but they did it awfully soon, a second after the Big Bang, which implies we can have a picture older than the cosmic microwave background. And I'm leaving something unsaid. Although the microwave background seems to have a smooth aspect, if your measuring devices are precise enough, you'll notice that it is not really like that there are tiny differences in the color. These differences are like the holy grail for cosmologists, but we'll talk about that in another video. And if you want more science, you just have to subscribe. And thanks for watching.